Okay, take a quick look around you. Everything you can see, everything you are, it's all held together by these invisible forces. Today, we're going to pull back the curtain and uncover the secrets of these forces. And believe it or not, it all starts with a single atom's quest to find a little stability. Seriously, have you ever thought about it? The water you drink, the air you breathe, the phone in your hand, it's all just a giant collection of tiny, tiny atoms. So what's stopping everything from just poof, drifting apart? Well, the secret is something called a chemical bond. It's the fundamental glue of our entire universe. And to really get a handle on that glue, we first got to meet the main characters in our story, the tiny particles that make up every single atom. So, inside the atom's core, you've got the heavyweights, the positive proton and the neutral neutron. But the real star of our show, the particle that makes all the action happen, is the tiny, negatively charged electron. It's this clash of personalities, especially their charges, that really sets the stage for everything. This setup gives us the atom's basic structure, right? You have this tiny, dense, positively charged nucleus at the center, and then you have these super lightweight negative electrons just zipping around it. It's a total classic case of opposites attract, and that attraction is what holds the atom itself together. Now, if an atom had an ID card, this would be it. The atomic number. It's just the number of protons, but it's everything. It's what defines an element. You got 6 protons? You're carbon. Always. Got 11? You're sodium. It is the atom's unchangeable identity. And this is where people sometimes get a little tripped up. If the protons define the element, what happens if you mess with the number of neutrons? Well, you get an isotope. It's still the exact same element. It's still carbon, for instance. It's just a slightly heavier or lighter version of it. Same identity, different weight. Okay, so we've met the players, we know who they are, but what makes them tick? What's their motivation? It turns out most atoms are actually kind of unstable. They're not happy just as they are. They're on a constant quest, and it's all driven by their electrons. This is it. This is the central question of all of chemistry. Why do things react? Why do things bond? It's not random at all. There is a single, incredibly powerful motivation driving almost every chemical interaction you can think of. And here's the secret. It all comes down to the noble gases. On the far right of the periodic table? Think of them as the cool kids. They are incredibly stable, totally unreactive, because their outermost electron shell is completely full. Most atoms want 8 electrons in that outer shell. That's the famous octet rule. And the noble gases are pretty much the only ones who naturally have it. They've already reached a state of chemical zen. So for every other element on the periodic table, the game is simple. Be more like a noble gas. They all want that full outer shell of electrons. A full outer shell is a happy, stable outer shell. And that desire, that quest for stability, is the engine that drives every single chemical reaction in the cosmos. So how do they do it? How do they get that full shell? Well, atoms basically have 2 main strategies they can use. They can either transfer electrons, a simple give and take, or they can cooperate and decide to share them. Let's start with the first strategy, the transfer. Think of it like a business transaction. One atom gives, another one takes, and the result is what we call an ionic bond. The key word here is transfer. A complete, total, permanent transfer. This isn't a loan and it's not a share. One atom literally hands over one or more of its electrons to another atom, and in doing so, both of them are changed forever. Okay, let's look at sodium. It starts with 11 positive protons and 11 negative electrons, so its net charge is 0. It's neutral. But here's the problem. In its outermost electron shell, it has just one lonely little electron. And these outer electrons, by the way, we call them valence electrons. They're the only ones that matter for bonding. So to get stable, sodium has a choice. Does it try to find and gain 7 more electrons? Or does it just get rid of this one? It takes way, way less energy to just give that one away. And that's the deal for a lot of metals. It's just easier to give away the few valence electrons they have. So sodium looks around for a partner, an atom like chlorine that is desperately looking for just one more electron to complete its outer shell. By donating that electron, they both get exactly what they want. It's a win-win. And would you look at sodium now? It's still got its 11 positive protons, but now it only has 10 negative electrons. So it has a net positive charge. It's not a neutral atom anymore. It's a positive ion. And most importantly, its new outermost shell is completely full, mission accomplished, stability achieved. And here's the final beautiful piece of the puzzle. That brand new positive sodium ion and its partner, the chlorine that accepted the electron to become a negative chloride ion, are now powerfully attracted to each other. Opposites attract, right? This electric force pulls them together into this highly organized, perfectly repeating structure, a crystal lattice. You probably know it by another name, table salt. But what if an atom doesn't want to give up its electrons? What if it's easier to just cooperate? Well, that brings us to our second big strategy. Sharing is caring. This is the cooperative approach. In a covalent bond, two atoms, usually two atoms that both want to gain electrons, they just decide to share instead. And by sharing, they both get to count those shared electrons toward their own stable outer shells. It's a real partnership, a molecular handshake. A fantastic example is the nitrogen gas that makes up like 80% of the air you're breathing right now. A single nitrogen atom needs 3 more electrons to be stable. So what does it do? 2 nitrogen atoms come together and form a powerhouse partnership. They don't share 1 pair of electrons or even 2. They share 3 pairs, forming an incredibly strong triple covalent bond that is super difficult to break. So atoms give, they take, they share electrons. It's a whole microscopic drama. But why does any of this matter in our big, everyday world? Because the type of bond an atom decides to form, that decision determines the properties of literally everything around us. Just think about it for a second. That powerful, rigid, magnetic-like attraction in ionic compounds, like salt, that's what creates hard, brittle solids with really high melting points. But covalent compounds, where you just have individual molecules linked together, they're often liquids or gases, like water and nitrogen, with much lower melting points. The type of bond directly shapes how a substance looks, feels, and acts in the real world. And, it doesn't even stop there. Beyond these super strong ionic and covalent bonds, there are also these other weaker forces that exist between whole molecules. And these subtle little attractions are also crucial. They often determine something as basic as whether a substance is a solid, a liquid, or a gas at room temperature. So from the salts on your food, to the air in your lungs, to the very DNA twisting inside your cells, it all just boils down to this simple atomic quest for stability. It really makes you wonder, doesn't it? If this one simple drive can build such incredible, breathtaking complexity, what else is our universe just waiting to build?